Okay guys, the last little bit of information that we're going to cover tonight about light is covering rainbows, mirages, diffraction, and polarization. Rainbows and mirages and polarization are all covered in your book in chapter 14 and 15, I think. Diffraction has its own chapter, chapter 16, but we're not going to get too much into it. I'm just going to tell you guys the concept behind it. So first thing, let's talk about mirages. So mirages are when light refracts in our atmosphere. So, when we talked about refraction before, we said that it was because the light was traveling from one medium to another. So, it was going from a solid to a gas or liquid to gas. But light can also refract when it goes into the same medium, but when it's two drastically different temperatures. So, if a beam of light is passing through air, and a patch of that air is cold, and then it hits a hotter patch of that air, it'll refract as well. Remember, refraction is what happens when the light slows down or speeds up, so it's changing its speed. So mirages happen when the ground above, or the air above the ground gets really hot. You usually see mirages when it's super hot outside, and that's because the ground is getting heated up by the sun, and all that air that sits right on top of the cement or right on top of the road gets hotter than the air around it. And so when the light passes through that warmer air, it will refract. What you end up getting is an effect that kind of looks like water, but in essence it looks like the reflection of the object above it. So it's almost like you're looking down on top of a pool of water because you can see what's above the object. And I have a couple of pictures here in a second if you guys have never seen a mirage. It kind of appears to us on the ground that the light is coming from the ground and not the sky. So, since the only time that we actually see an image directly below an object is when it's being reflected in the water, when we see this, automatically we think that there has to be water on the ground because we're seeing the object above it. So here's a little cartoon that shows you guys the phenomena of mirages. So some of the light that hits the tree gets reflected and goes right to your eye, but some of the reflected light goes towards the ground and it gets refracted down here where the ground is hot. And so the refracted light creates an image for us that looks like a reflection of the tree on the ground. So here are some pictures of mirages. You can see here it looks like pools of water on the cement, but those are not pools of water. That is just the light refracting due to the hotter air near the freeway down here. And same thing with this picture of the shuttle. It looks like the shuttle is sitting on a wet piece of cement, but it's not. It's just the mirage underneath it. Alright, rainbows. I spoke briefly about rainbows before. Rainbows are caused by refracted light refracting through raindrops in the air or moisture in the air. So, we sometimes call it dispersion when rainbows are formed. So since Snell's law depends on the index of refraction, remember the angle at which it is refracted changes depending on the wavelength. So, blue light has a much smaller wavelength than red light, remember, so if it has a smaller wavelength, it has a longer frequency or a greater frequency. So as it passes through mediums, it bends more than red light does. So when white light, or light from the sun, hits a prism, what happens is that the blue light bends more than the red light does because the wavelength is much smaller. So when the light comes out of the other side of the prism, it fans out in a big series of colors. It looks like a rainbow because each one of those different wavelengths refracts a different amount. So the purple or the blue light bends the most. You can see that really drastically in this picture. And the red light bends the least. So this little circle here represents a water droplet. As the light from the sun enters the water droplet, it will refract once. And it's actually refracting twice, once on the way in and once on the way back out. And so as it refracts, it is going to disperse into its different wavelengths here. And then as it refracts again, it's going to disperse one more time. And so you can see in this picture down here, the purple light is bending at a much greater angle than the red light. And so you get this fanning out effect here that creates the rainbow. So when you see a rainbow, the trick is that you have to have the sun behind you. If the sun is in front of you, you will never see a rainbow. And that's because the light has to come from the sun and refract through the droplets in such a way that you can actually see it. And the water droplets in the air, as each droplet falls, the light will refract through each droplet as it falls. So it looks like the rainbow's staying in place, even though we know that those water droplets are not just being suspended in air, right? Each one of those water droplets is falling. So it's just that they're falling kind of fast, and the light looks like it's not moving, even though the sunlight through each droplet is being refracted through each different droplet. Okay, so why are rainbows always in an arc shape? So when we see a rainbow, we typically see a rainbow that comes out in an arc, but in actuality, rainbows are circular. The problem is that we cannot usually see the bottom half of this circle because of the angle that the light's being refracted from the sun. So here's an example. If this is you and the sun is behind you, light is going to come from the sun, hit these water droplets, and become refracted. We're only going to see the top part here of this rainbow, but if we could see into the ground, we would be able to see all of it. It is possible to see a full circular rainbow sometimes if you are in a plane and you are traveling through kind of a misty, rainy storm, and you've got the sun on the other side of the plane as you. It's possible that you could look down and you can see a rainbow from the top, meaning that you will see the whole entire circle of the rainbow and not just the arc. So that's a pretty cool phenomenon. Not many people get to see it. All right, diffraction. Diffraction is the spreading of waves into a region behind an obstruction, or the bending of waves around a barrier or an obstacle. So all waves can diffract. Some kinds of waves do it better than others. Sound waves diffract pretty well. They can bend around corners and obstacles really easily. Light waves, most of the time, don't diffract around things very well. Light waves can sometimes go through things pretty easily, but not necessarily around the corner. So this is a picture of a sound wave diffracting. We've got this guy over here cleaning around the corner and a radio on the side. So if the radio were being played, he could hear the radio, but he couldn't see it. And that's because the light rays don't have a tendency to bend around things. Water waves can diffract too. This is a classic picture of diffraction where we have a small little slit here, and the water waves, as they pass through, the water waves are traveling this way. As they hit the barrier, they're going to filter through the opening here just a little bit at a time and then spread out to fill the space around them. So light waves diffract around obstacles. Like I said before, it doesn't do it quite as well as some other waves like sound waves. The amount of light that is actually diffracted around barriers is too small to be easily seen. This is a cool little app that I unfortunately cannot pull up on my computer because it is blocked due to the district search blockage. But if you guys can pull it up at your house, it's kind of cool because you can play with it. You can see refraction. You can choose to look at refraction. You can choose to look at different forms of interference, and you can take a look at what diffraction looks like through different openings and different barriers. And be sure to click on, watch it in the 2D mode, which means watching it from like the top here, but also click on the option for 3D because the pictures that you can see from that are pretty cool. This is just another example of diffraction. When light waves, or when any waves pass through an opening, they have a tendency to spread to fill the area that they're passing through. Sound does this incredibly, incredibly well. Okay, polarization. This is the last little thing I wanted to talk to you guys about today. Polarization happens primarily because light waves are traveling in a whole bunch of different directions. So when you think about the light waves that are bouncing around inside of a classroom, they don't all go one set way. They're all over the place. They are bouncing off walls, and not really very many of them are going in the same direction. We can do a process called polarization, where we force the light to go in one particular direction, or to vibrate in one direction. And when we can do that, we say that the light has been linearly polarized. That means it is going in one way. So here's a little example. Over here on this side, we have our crazy light waves. They are going in all different directions. They are vibrating around everywhere they possibly can. When they pass through what's called this polarizer, they're going to become linearly polarized, which means that all of those waves are only going to vibrate in one direction, and that is the vertical way. So if these vertical light waves tried to pass through a horizontal opening, they would not be able to do that. Polarization is a good way to block light rays, some light rays, from passing through openings or getting through barriers. We can polarize the light or polarize the film so that not all of the light gets through it. This is how polarized sunglasses work. Here we have a couple of examples. This picture is without polarized lenses, and then this is a picture with polarized lenses down here. You can see that the glare is gone, which is one big reason why people wear polarized sunglasses, to eliminate that glare. And that glare happens because all of the light is passing through your lenses. If you wear polarized lenses, not all of the light can get through it, and so you're left with not as bad of a picture. And then this is the same thing without polarized and with polarized. A lot of car windshields are polarized. If you wear polarized sunglasses, and some 3D glasses are actually polarized nowadays because the polarized 3D glasses are better. They show a better picture than normal blue and red 3D glasses. But if you wear the polarized 3D glasses and you go outside and look at your car window, you should see kind of bubbles, and those bubbles look like this. And what you're seeing in your polarized sunglasses is the polarized film in your windshield. So that's kind of a cool little effect. And that is all that I have for you guys tonight, and I will see you all tomorrow.